What I'll be talking about here is the work we've been doing at Manchester, predominantly Manchester and Exeter, at the use of the Aerodynamic Aerosol Classifier for optical work. What I'll be showing here is the work of a combination of a number of people. Want to specifically highlight Dawei Hu, who's my postdoc, who's been doing a lot of the bulk of the work that I'm going to be showing today, and also the folks at the Met Office, in particular Kate Speck, who has been helping out with the Excalibur instrument. So first of all, just a quick bit of motivation. I hope I don't have to sell this too hard about how the people within the climate community are very interested in light absorbing aerosols, particularly from combustion at the moment. And I must stress, aside all the usual motivation for global climate, these are particularly important for regional climate due to their short atmospheric lifetime. But at the moment, this is something we don't lack good predictive skill in climate modelling, and that's in part that's due to a whole range of factors. But one of them is that we are still in need of a good model to be able to link composition as predicted by a composition model with the optical properties we need in the radiative model. Now, there's a number of different ways of modeling the optical properties of particles. I've picked out 3 common ones used by the research community here. All of them just basically amount to providing a solution to Maxwell's equations for a given particle, given a certain geometry and refractive index. The one that is by far and away the most common one used is μ, which applies to spheres, specifically concentric spheres. This is very good in the fact that it's relatively computationally cheap and it gives you a nice unambiguous answer. But obviously, particles aren't necessarily spherical and concentric in the real world. So a more complex version is T-matrix. This is also in use by various parts of the community. And that's slightly more advanced in that you can use it to make arbitrary assemblages of spheres or even non-spherical shapes, depending on which configuration you're using. But unfortunately, you need to feed more information into that to get an answer. And then down at the bottom there, I've put the discrete dipole approximation, which you can just feed pretty much any geometry in that you want, but whether you get a sensible answer or not is another matter. This one obviously requires a lot more data and is hard to constrain, and is quite specialist and difficult to use. So the most common, as I say, model being used is μ, which you're using by modeling concentric spheres. You can also do mixtures, and we do know that black carbon particles tend to be mixtures. And there's various different approaches that you've seen in the literature that models the effect that the non-black carbon material can have in enhancing the absorption efficiency of the black carbon. Now, the simplest way is just modeling them as separate particles. You can also volume mix them, so you mix them all together homogeneously, which probably isn't physically meaningful for black carbon. Another one is kind of effective medium, such as the Maxwell-Garnett approximation. And then we have the coarse shell approximation, which assumes that the black carbon is just this kind of solid core right in the middle. There's a bit of debate about which one works, quote unquote, but I think really the debate should be on what's the most appropriate within the context of a climate model. Should say we published previously that would actually suggest that you may need to apply a kind of a hybrid model where you reach a kind of a threshold for the coating thickness and then switch between models to get the most realistic outcome. So the objectives of this work, this is the SASO project, a NERC-funded project. What we're trying to do is to use some new techniques and some new equipment to try to get out the appropriate parameters that we should be using in these climate models, which includes measurements of black and brown carbon. Now, the idea here, though, is not to really figure out which model works best. It's to kind of figure out what the most appropriate configuration for a ME model is going into a climate model. The reason is the as well as the computational expense, the other models require more variables to be input, which the climate models just don't carry. So what we're trying to do is trying to come up with a robust assessment of what the parameters are we should be using. And this is in tandem with kind of a planned upgrade to Haugen, which is the Met Office's main climate model. So what refractive indices should we be using? What mixing models should we be using? And what parameters best present subtle conglomerates when we're trying to model them as spheres? What we're going to be doing here is trying to critically assess all of these against the measured absorption and extinction in a laboratory setting. So the first experiment we've got is controlled wood combustion. This took place at Exeter. This builds on some previous work that we did. Normally, wood combustion tends to be quite not very, it's not very repeatable, and it produces very mixed aerosol. But some previous work we did showed that if you combust very small samples under controlled conditions, you can get repeatable work, but also that you can separate out the black and the organic carbon during the different combustion phases. We used a range of different wood types there at this facility at Exeter. Second experiments was with this diesel engine rig we have at Manchester. That was going through a catalytic stripper to leave bare black carbon. And then we're also using the Manchester aerosol chamber to generate secondary organic aerosols, with a view to creating secondary organic aerosols that don't absorb, so using alpha pinene, which is the usual go-to precursor. And then we also generated brown carbon SOA using cresol under high NOx conditions. And then, of course, by using combinations of the engine and the chamber, we were able to generate mixing states. And we also did a bit of ambient sampling as well. So the main measurement of the optical properties is the Excalibur instrument. This is developed at the Met Office mainly for airborne use, but we can also use it on the ground. This is basically a multi-channel instrument using photoacoustic spectroscopy and cavity ring down at multiple wavelengths. Not going to go into it in massive great big detail, but they uses multi-pass cells so for the photoacoustics, so there's good signal to noise ratio. For the actual instrument itself, I'd direct you to the various publications that have been produced on this in recent years. We also had a load of other instruments at our disposal. So we had the AMS and the SP2 for composition, measuring organics and black carbon, CPC for number concentrations. We had a DMS 500 for the high time resolution measurements. We had a HDMA, well, rather the humidification loop from a HDMA to try and force the soot to restructure. There's the shortwave spectrometer from the Met Office. That was on the burning experiments. And there's also a load of other stuff that was brought over for a separate Eurochamp experiment, which I'm not going to go into great big detail. This took place immediately prior to the SATO experiments at Manchester. One of the things we aim to do here is obviously optical properties depend very strongly on the size of the particles we're looking at. So ideally, you want to make the optical property measurements of a monodispersed cut. Now, the traditional method would be a differential mobility analyzer, but as I'll show, this has got issues relating to the multiple charging. And it is strictly measuring mobility diameter. So if you're looking at non-spherical particles like soot, it doesn't give you much in the way, it doesn't give you a realistic measure of geometry. We have the centrifugal particle mass analyzer that was talked about in the previous talk, which gives you a very accurate mass cut, but you still need to use a charger, so you still have the multiple charging problems. And then finally, we enter the Aerodynamic Aerosol Classifier. I'm not going to go into how this instrument works. I'll direct you on to combustion sales department for that. But the key thing here is it selects particles aerodynamically, but it does not rely on charging. That way we don't get any of these charging artifacts. Some people have used the approach running two classifiers in series, but that hits your throughput. To illustrate the issues that are brought on by multiple charging, this is taken from a paper that Michael Cottrell recently published. This is using a DMA in combination with Excalibur. And what you can see here, that for the extinction channel in particular, basically the extinction is dominated by the multiple charge states of the particles that you're sending it. So that's kind of not so much of a problem if you're looking at kind of pure component particles, where you know that irrespective of size, they're all the same composition. But it's far from ideal if we want to really home in on the small particles, as we do here. So setup that we have here is we've got our source of particles here. Now we have to send it through a dryer or a diluter, depending on which type of experiment we're doing, just to make sure that it's ready to be sampled by the equipment. The AMS, we're not able to run monodispersers because it's not sensitive enough, but everything else we send through the AAC. And then we have to send it through a diluter. That's just so we can match up the flow rates. And then we can send it to a range of other instruments here. The key things I pointed to here is we have the CPMA, a scanning CPMA with a CPC. Then that can give us the peak in the mass distribution, so it gives us the average mass per particle for this cut. The SMPS gives us our mobility diameter, which if the particles are spherical, which is an if, that will give us the physical diameter. And then we've got Excalibur measuring the optical properties with the CPC, so we can get the per particle optical properties, and an SP2 gives us per particle black carbon concentration. So the results just give you, this is just to give you a flavor of what we've done, because we're still very much in the process of analyzing the data right now. Well, this is a typical burning run that we did with the wood. Now, because this is a very small sample of wood that's being heated radiatively, and what happens is when you start the experiment, you start to initially produce these organic particles, which are from pyrolysis. So this is, start getting some smoke off there, but there's no fire. And then once it reaches a certain temperature, then what happens is the wood gets ignited. There's a little igniter above it. And then you start getting the flaming phase. And what we've found here, as with previous work we've done, is that this flaming, providing the flame covers the entire wood sample, it is more or less pure black carbon, as opposed to the usual mixture you get from a more complex fire. And then what we can do is part the way through the burn, we can snuff the flame out and introduce smoldering. So there we don't have a flame, but we still have combustion taking place, and we get some organic particles again. Very little black carbon, and we can, not shown here, but these are chemically different to the pyrolysis phase. So you can get two different types of organic matter here. And these different phases can vary with wood type, amount of moisture, and so on and so forth. And this is the same the DMS 500, where you can see these initial smoldering particles, these larger organic particles here. And then this is what a burn looks like when you sample with the DMS 500 downstream of an AAC. So this is with a single size cut of 200 nanometer particles. That's aerodynamic diameter, and you can see that we're getting different mobility diameters out of the DMS. So this is showing the effect of shape and density of these particles, and the fact that it's changing. And we can also see here, we've got these are the CPMA scans, and we can see that we have different mass per particles for the different phases for a single size cut, the AAC. So we're very much seeing the kind of effect of the change in composition physically as well. And then what we do with that, we have all this data. Now, I've got to stress here, this plot here, this is preliminary data. I'll ask you not to go running off with it, because I'm well aware that the implied refractive indices here are not realistic, but this is just preliminary data. We need to go over it a bit more. So please don't take it to the bank. I'm just using this to illustrate the next step in the calculation. So what we have here is brown carbon in SOA. We've got a measured mass absorption cross-section. So that's taking the Excalibur absorption, dividing it by the CPC concentration, and the mass per particle as measured by the CPMA, and same with the extinction as well. We have a volume equivalent diameter from the SMPS. We can trust that one because we think SOA particles are spherical. And then this is the wavelength of light we're using, 4 or 5 nanometers. This is in the blue. So we're looking at brown carbon here. And then what we can do is, by running a ME model at a variety of different refractive indices for this diameter, and then comparing the derived absorption and extinction with the measured values, and then plotting the residual, we can see a kind of like the kind of solution space in 2 dimensions. And what I'll draw you attention to here is this left-hand plot, which is showing absorption, is we've got a kind of like a range of refractive indices that sit up this graph here. These are values that it could be in terms of the real and the imaginary combinations. So it doesn't give us a discrete solution. But then if we go to the extinction, we've got again a kind of like a value in the residuals, but then this is kind of like in an opposite direction. Because the imaginary part of the refractive index affects absorption much more strongly. So this line's a lot more vertical, this line's a lot more horizontal. So the point here is to stress that by using the combination of extinction and absorption, we can then home in on the proper complex refractive index. Although I'll be the first to admit that the value we have here, which implies that the real part is in excess of 2, probably isn't realistic. So this is probably more due to the fact that our data is not fully quality assured yet, and we need to kind of go through it in more detail. And of course, on top of this, we can do things like sensitivity studies and so on. And then eventually, it's in a form where we could feed through to the models, but also to start evaluating the mixing models. So just to summarize, we used an aerodynamic aerosol classifier with a combination of a bunch of other instruments to get some very accurate physical and optical parameters for laboratory generated particles. And the key thing is there, without the multiple charge artifacts. We got 2 measurement campaigns that we're still in the process of churning through the data for, looking at wood burning, diesel engine and SOA and mixtures, and not gone into details here. There was also an associated experiment with folks from NRC Canada and Catholic Instruments, but that was a separate campaign. But these 2 were very matched up. So the next steps, we've got to finalize our experimental data, derive refractive indices, critically assess the optical mixing rules for multi-component particles. That's where the real fun is. And then critically assess representation of aggregates in a me model. This is for the sake of the climate model. So we're going to benchmark that against a more complex model like T-matrix. And also we're going to see, try and quantify the effect of restructuring using the humidification. So with that, I'd like to go to the acknowledgements. So funding by NERC, and also shout out to Catalytic Instruments who let us hold on to one of their strippers for longer than they originally planned. Yeah, any questions?
Yeah, we do have a couple questions. So Georgios, you're the first to raise your hand. So the floor is yours.
Thank you very much for the excellent presentation. I just wanted to ask you whether you have measured the fraction of organic carbon present in the combustion conditions that you presented, and how much did the MAC value, the mass absorption cross-section, changed in terms of the organic mass fraction that you produced?
Right, well, this is one of the, what I've got to kind of really stress here is the wood burning experiments we're doing are not meant to be simulations of real fires. So what we're trying to do is derive the optical properties for the individual components. That was the kind of primary objective here. And now what we did do in the later stages of the experiment is actually kind of, we kind of like upset the experimental setup for the sake of not getting a single component fire. So we're using kind of, you know, other materials for burning, and also setting the heater on the side. So we get like a frame front progressing across the sample. So we get mixed particles. But yes, we'll be looking for changes in the absorption by black carbon mass fraction, but we've not got quite to the point, we've not got to the point of analyzing that stage yet. We're working on the single components first. Don't know if that answers the question.
Let's assume so. If there's a follow-up on that, feel free to put that in the chat as well. We have a quick time for a quick question from Reza. So if you want to unmute yourself. Oh, there we go.
Hello, can you hear me?
Yep.
I can hear you.
Thanks a lot for your great presentation. I have a question about your MAC measurements, because if I understand it correctly, with the photoacoustic extinction measurements, you get absorption coefficient, and with CPC, you need the concentration data in order to convert it to MAC. And my question is, because these two are not synchronized, what is the best way to get accurate data? Should we measure concentration before we feed the particles into the optical chamber, or should we do it after it? And if you have any...
The setup we had was measuring the concentration after one of the optical, because the optical measurements are non-destructive, and we measured the concentration with the CPC immediately following the one of the optical tubes. I forget which one it was hooked up to. If Michael Cottrell's online, he might remember. The thing was, the reason we did that though is because the flow splitter setup in Excalibur was very well characterized, and they didn't want to mess with it. So it would give the most accurate, we decided it would give the most accurate measure by measuring downstream. But of course, you know, we needed to make sure that we characterized the optical cavity for losses as well, obviously.
Thank you.
Great. Thanks so much, James. And we are now going to move to our last presenter before our break.